It's a little bit of a mess right now because this hasn't been cleaned up ready for flight, but we can get some of the ideas. Right now we're looking at the back of the primary mirror. The inner frame can be steered in elevation. We apply a torque to this reaction wheel. You spin the reaction wheel to the right and the gondola will go to the left. So if you look really carefully, you can see that the gondola is in fact going back and forth by just a degree or something. So you can actually see what it's doing here on the screen, showing the path the blast would be mapping on the sky right now. So it's going back and forth, back and forth, back and forth. So it's almost up to the corner here, and it's going to turn around this and start scanning back the other way. And eventually, when it's all done, we'll be able to make a picture of this box on the sky. So when we make a map with blast, it's kind of like the reverse of an inkjet printer. You know, the inkjet printer goes back and forth and laying down ink. This goes backwards. We have our eyes that go back and forth, a map across the sky, and then we, in reverse, make a map out of it. Ed and David will have written a complete schedule file before we launch that, at this time, we're going to go look at this part of the sky, and then at this time, we're going to go look at this part of the sky. For fine pointing, there's a pair of star cameras.
These are the integrating star cameras, and they're the primary pointing sensors for blast. They mount up above the telescope on the inner frame. They take pictures of the stars, and from the positions of the star in that field, the camera will tell you where the telescope is pointed.
For power, we have these two sets of solar arrays, which charge these nickel metal hydride batteries when the sun is shining directly on them. In this cage back here is where the receiver goes, which is being worked on over there.
Now they're going to transfer liquid helium into the receiver. This has been a particularly hard campaign because we've had to do this maybe 5 times. It's a long process. Even a minor mistake can cost you a week. The way we make our measurements is we're essentially looking at something which is really quite cold.
We're going to go and look at these galaxies, but we're going to be looking at the dust, which gets emitted at a much colder temperature.
And so we have to have our detector very cold, so it's sensitive to seeing that. Compared to our detectors, it's blazing hot.
We had it open and warm so we could work inside of it. And now it would take 30 hours to get cold. Considering it also took two and a half days before this to get it to this temperature. It takes a very long time. It takes about 5 days to get it cold.
We have to align the optics box so that everything's in focus. What we've put in here is this really nifty laser that has a hologram in the front. So not only does it have the central spot, but it also projects this grid pattern that then bounces through our optics. We use this to make sure everything's aligned up.
Oh, the filters cost about $2,000 a piece. In fact, if you look at them, this is one of the smaller ones. It's actually a cheaper one. You can barely see it, but what's there is a bunch of wires which are only a few microns in diameter. That's a few millionths of a meter in diameter. And there's thousands and thousands of them. They're all parallel to each other. And they only let light of one polarization through, very much the same way your polarized sunglasses work.
The computer which controls everything is here in this pressure vessel. It's 2 completely redundant systems, so that if one goes down, the other one takes over. We don't want to ever be out of control of the telescope during the flight.
This basically gives us an overview of the gondola in terms of a state of health display, all the stuff that doesn't give us any science but tells us what the gondola is doing. So it gives our point of the sky we're looking at. We can get latitude, longitude, our altitude, how fast we're moving. We have a lot of sensors now for our power system to make sure we aren't going to explode our batteries, make sure that the batteries aren't going to run out of power, general housekeeping stuff like that. These are the kind of sensors that if the flight goes fine, we're never going to look at them. But if there's some problem, this is what's going to tell us.
Bart wrote some fantastic software with his students and is doing a great job.
We went with a Lord of the Rings theme this time around. So for instance, this computer here is Eowyn, and this one here is Elrond. The name of the program is Palantir, and so you have a little icon here. Saruman's using the Palantir to look into the future. It glows when we're getting data, and it turns black when we're not. And we've got over here the 3 trolls from The Hobbit. The flight computers are Frodo and Sam, because they're carrying the ring into Mordor there. And they're in a pressure vessel, because we need to keep the disks at atmospheric pressure.
Before we launch the telescope, on the ground we would like to have some estimate of what its sensitivity is to submillimeter light. The way you do that is to take a submillimeter light source, and what we've been trying to use is nitrogen, and sticking that in front of the telescope. So we only have some rough measurements that we've done here in the lab and extrapolating to what we would see focused to infinity. Because we're focused at infinity, we would have to put our calibration source really far away from the telescope, about 5 kilometers. The problem is, if you put a source really far away from the telescope, there's no way you can see it because the atmosphere absorbs all the 7mm light. We don't have a really accurate measurement of what the sensitivity of the telescope is.
See that?
There's this issue of being in the near field or far field of an instrument. And you can think of it as blinking your eyes back and forth. There's the camera 1, camera 2 thing. And if there's an object very near you, it flips back and forth against the background. So you see it from 2 different perspectives. Our telescope is 2 meters in diameter, and it is observing what's out there from these 2 very different perspectives. So imagine your eyes were spread out by 2 meters and you did the camera 1, camera 2 thing. Well, your finger would have to get really far away from you before you didn't see it perceptibly move against the background. For our telescope, that happens to be many kilometers away, so that is not an effect. Because the atmosphere absorbs the light many kilometers away, which is why we're flying on a balloon, we're forced to test it in the near field.
For a little while, can you give us the on-off if you're chopping?
Ready, fine.
On, off, on, off, on.
Where everything is completely distorted being too close.
On, off. See nothing. Off. On, big on.
See that?
Cool.
We're not going to know how this thing works until we are at float and start looking at sources. And there's going to be an awful lot of nerves when we start making the scan on that first source. Are we going to see it? Is it going to be compact? Is it going to be bright? Is the instrument working like it should be? And it's going to be exciting and really stressful.